Hi, I'm Mike Danielchuk. This paper addresses a common problem in robot grasping, false negatives due to overly conservative point contact models. We propose a new approach to more realistic finite area contact models based on an efficient formulation of 6D friction cones. With the rise of e-commerce, robots are increasingly in demand in industrial warehouse environments for the task of grasping a diverse set of objects. When geometric information for the object to be grasped is known, for example, a 3D CAD model, analytic techniques such as those in the left two columns can be used to analyze the forces and torques applied at the contacts that the gripper makes with the object. These techniques can also be used as part of a hybrid technique that labels grasp success to train a deep neural network that predicts grasp quality, as shown in the right column. To find the robust grasp quality for a given grasp, the grasp pose can be perturbed, and the resulting grasp quality scores are averaged. For each perturbation, a different set of contacts on the object and their corresponding friction constraints can be found and used to evaluate a grasp quality metric such as wrench resistance. As the contact profile is typically very complex for objects with fine surface geometries, existing contact models usually assume point contacts, as shown on the left. However, point contacts are a very crude approximation of the actual contact profile that occurs between compliant jaws and a rigid object. This approximation can result in many false negative predictions where the model predicts a grasp failure when the grasp succeeds in physical trials. Both videos show examples of false negative predictions with a point contact model in physical trials. Finite element analysis can better approximate the contact profile, but lacks computational efficiency. Similarly, the recently proposed REACH model can efficiently extract the contact area, but results in friction constraints that can be infeasible to evaluate when the contact geometry mesh contains many triangular faces. In this paper, we aim to reduce the number of false negative grasp quality predictions from point contact models while improving on the computational efficiency of existing area contact models. To do this, we extend the idea of a 3D friction cone to 6 dimensions. Point contacts use the friction cone to express that the frictional forces at the contact point are limited equally in the plane and scale with the amount of normal force that is applied. We construct a 6D friction cone for non-planar area contacts that expresses limits for the entire friction wrench, forces and torques in all 3 dimensions, and scales with the normal wrench that is applied at the contact. A 3D projection of the 6D cone is shown here. Coulomb friction states that the friction wrench applied at a point contact is a circle, where a wrench is a concatenated force and torque vector. The radius of the circle is proportional to the normal wrench. The total wrench applied at the contact is then the sum of the friction and normal wrenches, and is the circle that defines the friction wrench shifted along the normal wrench. Varying the magnitude of the normal wrench leads to a 3D friction cone, which is used to constrain the total wrench applied at the contact. Point contacts can be easily extended in the case of planar area contacts, as shown on the left. An additional torsional friction can now be transmitted through the contact and leads to 3D friction wrenches, which are constrained by a 3D ellipsoid. Similarly to the point contact case, this 3D ellipsoid scales with the normal force that is applied, and thus the total wrench can be constrained by a 4D friction cone. Grasping with compliant gripper jaws on a non-planar surface leads to non-planar area contacts, shown here on the left. For such contacts, the normal and friction wrenches are both 6D and can be constrained by a 6D ellipsoidal limit surface. On the right, we show a 3D projection of the 6D ellipsoid. The ellipsoid is typically not axis aligned, since the chosen axes for the contact are typically defined with respect to the gripper approach vector, and when one dimension of the friction wrench reaches its maximum, it does not imply that the other dimensions are 0, as in the planar case. To model the maximal total wrench for grasp analysis, this ellipsoid is then typically scaled with the largest closing force and shifted by the scaled normal wrench. However, this does not consider the closing forces between 0 and maximum, as in the point contact case. We thus construct the 6D friction cone by varying the closing force from 0 up to its maximum value, as in the 3D case, covering the full range of 6D ellipsoids for each closing force. To incorporate these 6D friction cone constraints into a grasp planning pipeline, we first efficiently extract the contact profile using a constructive solid geometry intersection. We then construct the 6D friction cone for the contact, convert the cone constraint into a set of linear constraints, and finally, solve a wrench resistance quadratic program that determines whether the contacts can resist a target wrench such as gravity. Specifically, once the contact profile is extracted, we sample pairs of points C and axes of rotation omega. For each pair, we first project omega onto each triangle in the contact area to find the friction wrench induced by an instantaneous velocity in the direction of omega. These projections typically correspond to a wrench with a large force component and small torque component. We then project the cross product of omega with the vector that points from C to the center of each triangle onto each triangle's face. These vectors circle about C in the plane perpendicular to omega, and thus the resulting frictional wrench caused by the instantaneous velocity typically has a large torque component and small force component. By summing these contributions to the frictional wrench at each triangle, we can determine the frictional wrench for each given omega C pair, which then corresponds to a point on the 6D limit surface shown on the right. After sampling many of these points, we can fit the 6D friction limit surface to a 6D ellipsoid using a least squares method. We then resample the points so they are evenly spread across the surface of the ellipsoid and capture the extremes. With even sampling, we can determine linear constraints that approximate the 6D friction cone to use in the QP for grasp quality. We analyze our method of finding contact wrench constraints as compared to previous methods through comprehensive physical experiments. We collect a dataset of 1,500 grasps on 12 3D printed objects using a compliant parallel jaw gripper with an ABB Yumi robot. Each grasp is attempted 5 times to estimate its robustness. We measure precision, which is inversely related to the number of false positive predictions, and recall, which is inversely related to the number of false negatives, as well as the runtime of each method. We see that 6DFC outperforms baselines in recall, which indicates it can successfully reduce the number of false negative predictions, while maintaining a similar precision to other methods. The runtime is comparable to that of the reach method, which considers only a fraction of the size of the contact area. Additionally, we test our method in comparison to the point contact model for a grasp planning experiment, in which the top grasps, as ranked by each method for each stable pose, are attempted. This video shows that in some cases, 6DFC plans a superior grasp that succeeds in a physical trial. However, there are also cases in which the point contact model outperforms the 6DFC model for grasp planning, as shown here. This case, as well as other false positive predictions from 6DFC, can occur from our assumption that the contact profile does not change across the duration of the grasp and that both jaws contact the object simultaneously. Dynamics in grasping also plays a large part in the resulting success or failure of the grasp, and is something that we hope to address in future work. In summary, we presented 6DFC, a new approach to more realistic finite area contact models for compliant grippers based on an efficient formulation of 6D friction cones. We show that 6DFC can help to address the problem of false negatives due to overly conservative point contact models. More details can be found at the website shown here and in the paper, and we welcome collaboration on this project in the future.